hello, hello. All right. Hello, everyone. Let's see, it's 11:02. I guess we'll get started. Are there any questions that you would like me to address at this point before we get started? Nope. Okay, so just as a reminder to bring this up. There it is. Okay, so just as a reminder, we are going to be covering today linear graphs with the slope-intercept method. We're going to do functions and functional notation, applications of linear functions, and maybe get to mixtures. We'll see. And then on Monday, remember, is our exam. So obviously today is not the exam. So Monday we'll have test 2, and it will cover everything from scientific notation on all the way down through wherever we stop today. So we can talk more about that at the end of class. I just want to make sure everyone's aware of where we are on the schedule. Okay, so last time we talked at the end about linear equations, and we talked about how when you have two variables in the equation, that what you actually have is what you actually have when you have two variables is a bunch of solutions, right? And all of your solutions are these ordered pairs, x and y. And so if we look at all the different ordered pairs that make the equation true, and we graph each one of those on a sheet of paper using the x and y coordinate system, if we graph all of them, then when we graph them, we will get a line, straight line. And that straight line represents the infinite number of dots together. So we just need to remember we have an infinite number of answers, right? For a linear equation of two variables, as opposed to linear equation with one variable where we have either one answer, no answers, or an infinite number of answers. We looked at 3 different cases that we could have. We could have a line like this that has kind of a slope to it. And whenever you see an equation that has both the x and the y in it, you're guaranteed that you're going to have some little pitch to the line. But if you see an equation that has just y equals a number, that it's going to be a horizontal line. And if you have an equation that has just x equals a number, you're going to have a vertical line. So that's kind of the gist of what we did last time. Now what we're going to do is look at the second way we can sketch lines. So we've already done the intercept method, and now what we're going to do is talk about the slope-intercept method. So to do this, I have to kind of set things up first. I have to kind of let you look at something. So I'm going to put a XY coordinate system in here for us. Okay, so here's our little graph paper, and I'm just going to draw some arbitrary line. So I'm just going to draw a line. Just going to make it up. Let's go with that one right there. Okay, so from this line, what I hope everyone can see is that this would be the case where both x and y appear in the equation. And that's because it has some pitch to it, right? It's not vertical, it's not horizontal. So because it has a little bit of a pitch to it, we know that x and y both appear in this equation. We don't know what the equation is yet, but we know that it's not y equals a number, x equals a number. Now, a very important point on this graph is that point right there. Now, that point is the Y-intercept. That's the Y-intercept. And can somebody tell me what we know about that point? Is there one of these coordinates? That's what we call those numbers. You know, this right here is called the x coordinate. And then this one is called the y coordinate. I'm just going to put chord. Can somebody tell me what the x coordinate or y coordinate of that point has to be?
Two.
Okay. I heard 2, I think. 2 would be what though?
Shouldn't it be 0 and then 2?
Okay, so your x coordinate would have to be 0. Does everyone agree that? Because if you're going to hit the y-axis, your x has to be 0. Do y'all agree?
Oh, yeah.
X has to be 0. Okay. So the y coordinate, you can tell from this picture that the y is 2, right? Because you just go up 2. But if I drew another line, let me just draw one by hand. If I draw a separate line and I say, okay, see that red dot? What can you tell me about that point? For sure, the x coordinate has to be 0 again, right? Now the y coordinate is going to be something, I don't know, whatever it is. But no matter what, no matter how I draw a line, no matter how I choose to do it, if we're going to talk about the y-intercept, then the x coordinate has to be 0. So I'm about to put an equation on the board here, and I want us to just take a look at this. All right, this right here is called the Slope-Intercept Form of a line. Okay, so I want to be able to contrast that with something else. So last class, I gave you something like, you know, we had something like this, and we would all look at that and we'd say, okay, that's a linear equation with 2 variables in it. We would, hopefully everyone would just look at that and be able to see that. It's a linear, it's an equation, it has 2 variables, x and y. So we know that the solutions to that should form a line. Now, the slope-intercept form is just another way of writing this equation right here. It's just another way of writing it. And what it is it's this equation, but you isolate the y. You isolate y by itself. So I'd like for us to just practice this real quick, and then we'll get into the details of why we would even want to do this, all right? But let's just actually see that if somebody gives us a line in the form from last class, that there is a way to transform it into this slope-intercept form. So all I'm going to do is take this equation here in yellow, and I'm going to try and get y by itself on one side of the equation.
So we minus 2?
Yeah, I'm going to minus 2x on both sides. The 2 x's are going to go away. I'll still have 3y equals, now on the right-hand side, I have 12 minus 2x, and I can't put those together. They're not like terms. So I'm going to write it backwards. So I'm putting the x in front of the number, and that's because if you look up at this slope-intercept form, notice that you have the x before this b. So wherever the x is, it goes first, and then whatever's left goes to the side. Okay, do we have y by itself?
No.
Not really. We have the 3 in front, right? So we're going to want to divide by 3 now, not subtract, right? We're going to divide everything by 3. And so on the other side of the equation, we have to divide every term by 3. So let's see what happens. We get y equals, okay, I have a negative 2 over 3, and I still had an x there. So I'm going to write it that way. And then I have plus 4. Okay, that right there is what we call the slope-intercept form of that line. So I'm going to go back up and erase this. So the one that we started with, this is called the standard form. And all we've done to get from here down to here is converted it into the slope-intercept Slope-Intercept Form. I'm just going to put Slope-Int. Okay, that's the Slope-Intercept Form of the line. Okay, so why is this useful? What's the point? Well, do you remember over here where we started this whole conversation? We said, if you have any line and you look at the y-intercept, right? You can guarantee me that for any line, the y-intercept is going to happen when x is 0. So whenever x is 0, right, that's what will determine what the y-intercept is. So I'd like for you to look at this equation that we just came up with, the slope-intercept form right there. Okay, and I want everyone to recognize that it matches what we have up here. Okay, we have y equal to, we have a number in front of x. That number in front of x is m. And then we have a number by itself over here, that's our b. Does everyone see how that matches the generic form up here? Y equals mx plus b. You all see how we can see what b is, we can see what m is. Does anyone tell me what m is and what b is?
M is the -2 over 3.
Yep, and it's just the number, it's not the x, right? So it's just the -2 over 3, and then the b for us is the 4. Right?
You got the 4 because you did simplify the 12 over 3?
Yeah, I just did 12 divided by 3. Yep. Okay, so let's I'm gonna write it down again one more time. Okay, so remember, let's say I wanted you to find the y-intercept of this line right here. If you were trying to find the y-intercept, you would replace x with 0, right? That's what this is saying. This picture over here is saying, hey, if we want to find the y-intercept, we know x has to be 0. And then from last class, we also know that when we try and find y-intercepts, we just set x equal to 0. So what would happen if you set x equal to 0 in this equation right here? What would you be left with?
The 4.
Just the 4, right? Just the 4. In fact, if I write the general form like this of a line in slope-intercept form, this y equals mx plus b, then if I ask you to find the y-intercept, you're always going to replace that x with 0, right? And it's always going to kill this off every single time. It will kill that mx off, and you'll always be left with the b, no matter what, right? The b will always be the y-intercept. Does that make sense? Because this front piece will go away. So what I'm saying, if you want to just kind of like take one thing away from this, is that whenever you're looking at a line that's written in slope-intercept form, the b is always the y-intercept. The number that's sitting out there by itself will always be where your line hits the y-axis, every single time. So long as you've solved for y, it'll always be that way. Okay, well, how does that help us? Well, it helps us because we want to graph this, right? That's our ultimate goal, is to graph this line. So by looking at that equation, okay, by looking at this equation, if I were to just tell you, hey, everyone, look at that equation right there, y equals -2/3 x plus 4, we know that the 4 is the y-intercept. So I can just go 1, 2, 3, 4, and I can just put a dot there. And I know that that dot for sure is part of my line, right? Guaranteed. So what's the only other thing I need to be able to draw this line? We talked about this last class. What are the 2 things you need to draw a line?
Intersects?
Yeah, but if I just asked you to draw a line, I would only have to give you 2 points. Right?
Yeah, 2 points.
2 points, and then you can draw a straight line. So we have 1. We just need one more point. And the other point is going to come from this m that's in front, the -2/3. We refer to this as the slope of the line. Okay, so the m in front is always what we call our slope. And the slope has to do with the pitch of the line. So the way this works is that M, and I know a lot of you have seen this, M is called the slope. And it is referred to, or it is written as a fraction as the rise over the run. You all heard that before? Rise over run. So I'm gonna write down the fraction we have here, -2/3. And I'm gonna just work through this one, and then hopefully after I do a few of these, it'll start to make sense. So we have one point right there. We already have the y-intercept. We just need one other point to draw the line. And this number, -2/3, is going to be what tells us, or this is going to tell us how to get to another point. The number on top is how much we go up or down by. If it's a positive number, we go up. If it's a negative number, we go down. So in this case, it's a negative number, right? So we are going to go from this point. Okay, we have to start at the y-intercept. We need to go down 2 spots. So 1, 2. So I'm going down 2. And then we look at the bottom number 3. This is what we call our run, and that's always our left and right movement. So if it's positive, we're going to go right. If it's negative, we're going to go left. So in this case, we want to now move which direction? 3 spaces.
The right.
To the right, 3 spaces. 1, 2, 3. So we've gone down 2 over 3, and once we get to that position, we mark a dot, and then we draw our line. I missed it, but you get the idea. Okay, so this is very different than the method from last time. Last time, what we did is we found the x-intercept, we found the y-intercept, and we drew our line. Here, we're finding the y-intercept, okay, by just looking at the equation, and then from there using this rise over run to get to another point. All right, let's do a brand new problem. And I think I'm going to go to the packet to do this one. Okay, so let's look at this first one. 2y equals 3x plus 8. I'm going to do this on a new page. 2y equals 3x plus 8. Okay, is that a linear equation in 2 variables?
Yes.
Yes, okay, so is it in slope-intercept form? Is it solved for y?
No.
No. What do we have to do to solve for y?
Get the y by itself.
Y by itself. So we divide both sides by 2, 2, 2. So we should get y equals, I'm going to watch how I write this. 3 halves, 3 over 2x, plus 8 over 2, 8 divided by 2 is 4. So there it is. There's our linear equation in 2 variables written in slope-intercept form. So can we identify the important parts? What's M for us and what's B for us?
So m is 3 over 2.
3 over 2, and B is
4.
4. Okay, so now let's go and try and sketch this line. So we always start with the y-intercept. And the y-intercept for us is 4. So we're going to move up 4. 1, 2, 3, 4. We're going to put a dot. So we have 1 point. Now we need the second one. So now we go to our slope, which is our rise over run. What does the 3 on top tell me we need to do?
Go up 3.
We're going to go up 3. And then what does the 2 on the bottom say? Right 2. So I'm going to do that. And where do we start? Where do we start going up 3 and right 2? Where do we start from?
The y-axis.
The y-intercept. We always start from that point that we had. Yep. So we're going to go up 3. 1, 2, 3. And then we're going to go to the right 2. 1, 2. And right there, we're going to slap a dot. And then to the best of our ability, we're going to draw a straight line. Now, does this method give us the x-intercept? But can we tell what the x-intercept is easily with this method? And we know what the y-intercept is, right? It's 4. But do we know what the x-intercept is?
No, not easily.
Not really, right? Like we might guess as to where that's hitting, but I mean, we'd really need a straight edge to get a good idea, but that's okay. I mean, that's not the point of this method. This method is supposed to be fast if you have your equation solved for y. So then it's just like, boom, you just find your y-intercept, rise over run, and you're done. Let's do another one. We'll do 2, -3y. Oh, you know what? Let's do 4, sorry. 6x minus 3y equals 9. Okay, this is definitely not in slope-intercept form. This is in standard form. So let's switch it over to slope-intercept form. So I will subtract 6x on both sides. When I do that, I'm still going to have -3y. And I'm going to have, watch how I write this, -6x plus 9. Now it's plus 9 because that was a positive 9 on the right-hand side. What would my next step be?
Isolate the y.
Isolate y, so do what?
Divide.
Divide by -3, -3, -3. So everything gets divided by -3. You should have a y here equals, now just be careful with your signs here. On the first one here, we have a -6 over -3. A negative over negative is positive. So we should get just, what, 2x there? And then be real careful on this because this is positive 9 divided by -3. What is that?
-3.
-3. Okay. So now we should be able to now just look at that and identify the slope and the y-intercept. Let's start with the y-intercept because it's usually a little easier. So what's our y-intercept here?
The -3.
-3, good. You have to include the sign. So if it's positive, positive of +3, we would have said just 3. But because it's -3, we're going to put -3. And then what is the slope? This one's a little bit tricky.
2/1.
Yeah, you have to rewrite this 2 as a fraction. But we can always write a number as itself over 1, and that would be a fraction. So that tells us that we're going to go up 2 into the right 1. And I think we're ready to draw. Any questions while I'm setting this up here? So I'm going to go to -3. See that the y-intercept, I go down 1, 2, 3. There's -3. I draw a dot. And then from that point, I'm going to go up 2 to the right 1. So up 2, 1, 2 to the right 1. Boom, drop a dot.
2.
And then I could draw my straight line. If I wanted to, I could do it again. I could go up 2 to the right 1. I could draw another dot. Up 2 to the right 1, draw another. I could do that forever. All of these will lie on a straight line. Oh my God, that's terrible. Okay, good enough, I guess. They should all lie on a straight line. If I had a ruler, I could verify that, but. Okay. Any questions?
I made the mistake of going up instead of down.
Oh, for the
Just
3
up
for the
to-
y-intercept?
Yeah.
For the y-intercept? Yeah. Just be careful. I see all kinds of things. People will take this -3 and they'll go to the left 3 and put it there. So they accidentally do it as an x-intercept instead of y-intercept. It's always the y-intercept. So do y'all see why they call this form of the line the slope-intercept form? Does it make sense why we call it the slope-intercept form? I mean, doesn't it just tell you just that number is your slope, right? And that number right there is your y-intercept. So that's why it's referred to as the slope-intercept form. Okay, let's see what else we got here. Why don't we do one of these that has some fractions in it? let's do number 12. I should be able to work this right here on this page. Okay, so number 12, is that in slope-intercept form?
No.
No, it is not. Okay, so the first thing I'm going to do is I'm going to get the y by itself. So I'm going to subtract 1/4 x on both sides. Okay, and that'll just have the effect of killing it off on the left. I'll still have 1/2 y equals, now on the right side, I'll have negative 1/4 x, and then I'll have minus 2/3. Now I don't have y, I have 1/2 y, right? So I need to get rid of the 1/2. So I can either divide by 1/2, or what would be another way I could do it other than dividing by 1/2?
You could multiply everything by a certain number.
Yep, I could multiply everything by, in this case, 2, because that would kill off the 2 that's down here, right? So just multiply that. But whatever I do on that side, I have to do on the other side too. So I have to multiply both sides by 2. And I have to have that in parentheses so the 2 distributes. So the 2.5 are going to go away. I'll just get y. And then we distribute through here. Now I'm only going to do the first one. I'll only show the first one. I'm doing 2/1 times negative 1/4. So that's that first multiplication. And that's going to give me negative 2/4, which reduces to be negative 1/2. So I'm going to wind up with negative 1/2 x. And then does someone want to tell me what the next distribution would be? You multiply the negative 2/3 times 2?
2/1.
What'd you say?
You do the negative
I'm
2/3.
talking about this one right here.
Oh, okay.
Multiply that. Go straight across. Minus. Anybody?
2.
Sure, we're doing 2 times 2/3, right? Or you could say negative 2/3 if you want. That's same as
You have to put a 1 under the 2, right? Oh.
Yep, so that's the same as this. And we're multiplying, right? Multiplying. Negative 4/3. So I'm going to put minus 4/3. There we go. Now we have it. Now we have it. This allows us to identify our slope and our y-intercept. So our y-intercept is negative 4/3, and our slope is negative 1/2. Okay, so this is the first time we've actually run into a problem where our y-intercept is a fraction. And that might be a little bit problematic because as a decimal, this is approximately negative 1.333 forever. Okay, so you've got on your calculator and did that. That's going to be hard to put on this graph, right? Like, where do you put that? And in fact, I don't even like that graph. That graph doesn't allow me much room because negative 1.3, there's negative 1. I don't know if y'all can even see that. Let me zoom in on that. Oh, wow, that didn't work. Where's it? There it is. It's really hard to put this in here. Here's negative 1, here's negative 2. So negative 1.3 is like, I don't know, somewhere around here. It's hard to figure out exactly where to put it. So you're just going to have to kind of ballpark it, if you know what I mean there. And then where do I go from that point? What's my rise and my run here? It's right there. Right?
You got to go up negative 1.
Okay, so up negative 1 really means down 1, right?
Yeah, down 1.
And then right 2. Okay, so I'm going to go down 1 and to the right 2. So this is where I was saying it's kind of hard to do this. Down 1, and I was going to put me about like right there. And then to the right 2, put me about right there. So I'm going to put like this, and then I'm going to draw a straight line through there. Do you see how that's a little more challenging? When your y-intercept is not a nice number, then you have to kind of estimate it, and then you're up and, you know, up, down, left, right from there is a little bit weird. Any questions on that? So we could go through some more examples, but let me ask you something. We now have two ways of graphing a line, right? We've given you two different methods. Which one do you like better? Or do you care? Which one seems easier to you, you know?
This one seems easier than the other one.
Okay.
Less work, I think. Maybe.
Everybody has their own preference. Like some people will tell me they don't like this method and they like the other one. Some people tell me the opposite. So on your exam, like in your homework, it's going to tell you, like in the homework, it says, use the slope-intercept method to graph the following. So they want you to solve for y and do all that stuff. On your exam on Monday, I'm going to ask you to graph, you know, several lines, but I'm not going to tell you which way you have to use. Like it's going to be completely up to you. All right. If you want to use the intercept method, go ahead. If you want to use the slope intercept method, you go ahead and do that. So that way you have the freedom and flexibility, because either way you should get the same answer. Like
That's
you'll
what I was
draw
gonna
the
say.
same line.
You get the same answer using both
Yep.
methods? Oh, okay.
Yep. Yep. What happens is later on in math, when we start talking about functions, whenever you talk about a function, in general, a function is always solved for y. So later on down the road in calculus and things like that, or pre-calculus, we're always looking at things that look like y equals something. So if you're looking at a line, it's gonna be in slope-intercept form. So it's like that's, you're gonna wind up using this method that we're doing today later on in further math classes, which of course y'all are not gonna be doing, so it's not that important. So that's why I don't mind which method you use. Okay. Okay, take a look at this question. You know what, hold on. Yeah, okay, let's do this one, number 13. So write this line in slope-intercept form. So to do that, all I need to do is get y by itself. So I'm just going to add 4x to both sides. And it goes away, so I just get y equals just 4x. That's weird. Okay, can you tell me what m is? Can you tell me what b is? So do you know what the slope is?
The slope is 4.
Okay, but we have to write it as a
One.
fraction.
Oh,
4 over 1.
Yeah.
Okay. All right, now what about the y-intercept?
It's 0.
Yeah, good. So there's really nothing out here, right? Plus nothing. So you have to realize here that the y-intercept is 0. Even though it wasn't written, it's understood that it's there. So just looking at this, I know my y-intercept, I actually don't go up or down at all. So it just stays there at that point in the center, which we call the origin. We start there, and then from there, we will go up 4 and to the right 1. So I go up 1, 2, 3, 4 to the right 1, and I put a dot there, and I draw the line. Jeez. Right? Like that. Okay. Can you tell me what the x-intercept of this line is, just by looking? Where does this line hit the x-axis?
0.
At 0. And of course, we know the y-intercept was 0 also. I'm answering this question. It wants us to find both the x and y-intercept, so I'm answering that. And then this last part of the question is, what can you do to find another point on the graph? Well, we can just do the slope, right? Up 4 over 1, up 4 over 1. So we can use the slope. The answer to that second part would be, use the slope up 4 over 1 to find another point. Okay, so now this next part, we need to discuss this. So I'm going to go to a new page here. So we're going to take a slightly different perspective now on things. Up to this point, I've been giving you an equation, and I've been asking you to draw a line, right? So I give you an equation, a linear equation, 2 variables, say, okay, take this and draw the line. You have 2 different methods to do that. This is different. What I'm going to do now is I'm going to give you 2 points on a line. Okay, so I'm going to tell you this point, 1, 2, 3, 7. This is the point 7, 7. And this is the point -3, 2. Okay, so that's given to you. You have 2 points. Now, my question is, can you tell me the slope? Find the slope. Find the slope. Well, think about it. If these points live on a line, right? If these points live on a line, then we can always use the slope to go from one point to the next. So how much did you have to go up by here? What was your rise in order to go from that one point to the other? Can you tell me what that rise was?
4.
5.
Looks like
Oh.
5,
Oh,
right? You can count it out, but it's
5,
5. Our rise was 5, and then what was our run? What was the distance we went over?
10.
It was 10. Okay, so you could get that just by counting, all right? But there's an easier way to get it. And the way you get it is by first looking at the y coordinates. Look at that 7 and that 2. Do you agree that those are the differences in the y coordinates? So on the second point, right, the 7, 7, you've gone up, up to 7 on the y coordinate, but you started at 2. So would you agree that the rise would just be 7 minus 2? It's just the difference of those. Do y'all agree with that? 7 take away 2, that's where you get the 5 from. And then the run, this one's a little tricky, is just the difference of the x's. So the x on the first point is 7, or sorry, on the top right point is 7. If I take away from that, what's the x on the second, or on the other point over here? It's -3, right? So you take away -3. So you would get a rise of 5 and a run of 10, because 7 minus -3 would be 7 plus 3, which is 10. Do y'all see how I kind of did that? The difference of the y coordinates would give you the rise. The difference of the x coordinates would give you the run. Now, I have another way I'm going to give this to you. I just wanted you to kind of see it first. I'm going to draw this more abstractly. So let's say I start off and I give you 2 points. Okay, so this first point and this second point. Okay, so 2 points here. Now I'm going to tell you that the x coordinate of this point here on the left, I'm going to say, I'm not going to tell you what it is. I'm going to just call it x1. And then the y coordinate, I'm not going to tell you what it is. I'm going to call it y sub 1. So those are little subscripts. And then over here, this other point, I'm going to call it x sub 2 and y sub 2. So do y'all understand what those subscripts represent, the 1 and the 2? It's like, this is the x, but for the first point. This is the y, but for the first point. And then this is the x for the second point. And this is the y for the second point. So that's all those subscripts are doing, is just distinguishing them from one another. So like I just said, if we want to know the slope, it's going to be the rise over the run but we said that's the difference of the y coordinates, which would mean you take this number y2 and you subtract y1. So I'm going to put y2 minus y1. And then you divide that by the run, which would be the x coordinate of the second point minus the x coordinate of the first point. So x sub 2 minus x sub 1. And that is a formula for the slope. So that you need to know. Give me just a second. Okay, so let's go back to the packet. And I'm going to jot the formula down here. If we ever want to find the slope, we just take the difference in the y coordinates and divide it by the difference in the x coordinates. So it says here to find the slope through these 2 points. So they give us 2 points, and they want to know what the slope of the line through those are. So what I'm going to start off doing is I'm going to label these points. I'm going to call this x1, y1, call this one x2, y2. Okay, so I'm choosing to label it that way. And now I just apply the formula. The slope should be, what's y2?
Oh, y2.
-3.
-3. And then I'm going to subtract from that what?
-2.
This -2, right? That's y1. So I'm subtracting a negative. Be real careful there. And then I'm going to do the x2 minus x1. So x2 is 8. And subtract from that x1, which is 6. Is that clear to everyone? What do I get? It's that top number. Careful. It's -3 plus 2, right? Negative is positive, or minus a negative. So -1 on top and 2 on the bottom. That's your slope. -1/2. Any questions?
So the answer would be -1/2.
Yeah, that's the slope of that line. Now, what would have happened, okay, if someone came in here and decided to do it the other way around? What if they said, I'm going to do x1 here, y1 here, and call this one x2 and y2? Are we going to get the same answer, or is it going to be a different answer? Because there's nothing telling you which point you have to call your first one and which one you have to call your second one. The formula doesn't tell you what you have to do. It just tells you once you determine what they are, just use the formula. So let's just do that under here. How would this change? I would have y2, which would be -2. I'd be subtracting y1, which would be -3. And then I would do x2, which is 6, and then I'd subtract x1, which is 8. So on the top, I get -2 plus 3. And on the bottom, I get 6 take away 8, I get -2. The top is +1, and the bottom is -2. Are those two answers the same or not?
No, they're opposite. I mean, they're not the same. Are they?
Think about it. Be careful with fractions. Something I talked about way early in the class. I said if you ever have a negative out in front of a fraction, that negative can be on the top or the negative can be on the bottom. All of those are the exact same expressions.
Oh, okay.
-1/2 is the same as -1/2, which is the same as 1 over -2. These are all equal to one another. So these two answers are the same. And it turns out that no matter how you do it, as long as you follow the formula, difference of the y coordinates over difference of the x coordinates, you will always get the correct slope. I think we should do one with the fraction. I like number 17. Number 17 looks good. So I'm going to call this first point x1, then y1 like that, and then this one x2, and then y2. Then I'm just going to apply the formula. So y2 is -4/7. And I'm going to subtract from that y1, which is 4/5. And then divide that by x2, which is 1/2, and then minus x1, which is 1. Do you all buy that? You agree with that? I'm going to turn off my video because I'm experimenting on something. Something is going on with my Zoom that when I turn off my video, it closes all of y'all's, like all of your videos. So let me see what happens here. See, it didn't do it that time. That's really weird.
It depends on if someone else is sharing their video feed or not.
Like if nobody is, then
If nobody else is, then that little sidebar thing will go away because Zoom realizes that there's no point showing that if no one's video is there.
yeah, that's probably what it is. Okay, thank you. Yeah, so Lorenzo, thank you for sharing your video. Okay, do we have any questions here on this M, like how I set this up? We've got to do this. This is going to be fraction stuff, right? So this goes back to stuff that we've already talked about. So the way I'm going to do this is I'm going to do that little cross multiply thing, like, you know, here to here, here to here. So I have to be careful with these signs. I'm going to get -20 and then -28 over 7 times 5, which is 35. Then all of that over, bigger division bar there. Here I have to rewrite that 1 as 1/1 and then do that little crossy thing. So I get 1 minus 2/2. So I'm trusting that all of you have done that enough where, you know, you could do that and get this correct, hopefully. So on the top, I'm going to have -48 over 35 over -1/2. And then remember, a fraction over a fraction is the same as division. So I can go -48 over 35 divided by -1/2. But division can be turned into multiplication if you do that. What was it? Keep.
Copy dot flip.
Yeah, copy dot flip. Thank you. Couldn't remember what that was yesterday or Monday. And
Yeah,
then
when I was watching your video, I kept saying copy dot flip, but you know, I was watching the recorded
Yeah.
video.
Yeah. -26 over -35. So I'm just multiplying straight across there. And the last, that's pretty much it unless we can reduce that, but I don't believe that reduces. So the best you could do is get rid of the two negatives because negative divided by negative is positive. So you could write -96 over 35 and that would be your slope. All right, any questions? I think that's it that I'll do for those. I think you can work with the rest. Just be careful with the fractions and be careful with your signs. You know, minus, minus, things like that. Okay, we need to talk about parallel and perpendicular lines. So let me ask you a question here. If you were to try and explain to somebody what two parallel lines were, how would you explain that to them? Just you're talking to someone and they've never seen or heard of a parallel line or two parallel lines. How would you explain it to them in layman's terms?
Just a line side by side.
Lines side by side? Okay, so
Going the same way, like
okay, like pointed kind of in the same direction. So, you know, these two lines are side by side. Are they parallel?
oh no,
Why aren't they parallel?
because they're going downward.
Because they'll eventually intercept.
Yeah,
Oh,
like if I continue this line and continue this line, like they're going to eventually intercept somewhere, right? Intersect each other. So there's something about parallel lines where you don't get that intersection, right? So would this be a good, pretty good, like, definition? Two lines are parallel if they don't intersect.
Oh, okay, yeah.
That sound pretty good?
Mm-hmm.
Okay, so, you know, there we have a line, no matter how you draw it, a line that's parallel to it has to have this quality to it that they won't hit each other. But what does that mean? I mean, in mathematical terms, what does that mean? What must be the same about those lines then?
Their slope.
Their slopes, what?
Is it same?
Their slopes have to be the same.
Yeah, their slopes have to be the same. Like if the slope of one of those lines is a little bit different than the other, then they're going to hit each other somewhere. So another way of saying this is that they must have equal slopes. Okay, the slopes must be equal. So let me kind of give you a general example of this. Let's say that we have a line, okay, and I'm going to call it L1, okay? And let's say that this line has this: y equals m1x plus b1. And then I haven't, just let me write this first, then I'll explain what I'm doing. Y equals m2x plus b2. So I'm giving you two lines that are written in slope-intercept form. Okay, so a specific example would be something like y equals 3x plus 4, and then y equals, let's say, negative 3x minus 5. I'm just giving, these are like specific examples. This is more of like in general. My question is, if this right here is given to you, two different lines, what would it take for you to be able to say that they're parallel? What would have to be equal? We just said what it was. But
Oh, you have to find the slope. See if the slope is equal.
yeah, we would have to compare these two slopes, right? We would need M1 to equal M2, right?
Yeah.
That's what it would take for parallel. If they're the same, right? So if M1 equals M2, they're parallel. So look at the specific example I gave you. Do you agree that in both of these equations that we are in slope-intercept form? We've solved for y, right?
Yeah.
So the slope of the first line is 3. What's the slope of the second line?
Oh, it's -3.
-3. Are those the same?
Oh no.
They're not. So are those two lines parallel?
Oh no, they're not.
They're not, okay? They would either both have to be 3 or they would both have to be -3, right?
Mm-hmm.
That's what it takes for two lines to be parallel. Okay, so let's look back in this packet. Let's look at these. Let's look at this number 20. Determine if the following lines are parallel, perpendicular, or neither. So look at line 1 and line 2. Are they written in slope-intercept form? Y equals mx plus b.
Yes.
Yes, okay. Can you tell me the slope of line 1?
The -2/5
Yep. And the slope of line 2?
is 5/2.
Okay, are those equal?
No.
No, so they are not parallel. We know that much. They might be perpendicular, but I haven't talked about perpendicular yet, right? But they're definitely not parallel. Yeah?
Right.
Okay. Now, I'm going to proceed and I'm going to talk about perpendicular, but I want to go off on a little tangent here just for a moment. You know, you all know that sometimes I like to go and just start talking about things that are kind of off topic. So we've established right now that two parallel lines will never intersect each other. So if you look back throughout history, if you look back to like the first, I want you to think about anything you've ever seen in terms of like cave drawings, like drawings that were done by humans in caves, like thousands and thousands of years ago. Would you say that their drawings were pretty good, or would you say that they were kind of like childish?
Childish.
Yeah, kind of like stick figure sort of thing,
Yeah.
right?
Mhm.
Not a very elaborate, not very elaborate drawings. So like if someone were to ask me to like draw a person, and I draw, you know, that, I mean, that's a pretty childish drawing, right? I mean, stick figure, big deal. Well, this has to do with parallel lines, all right? So if you go to an art gallery or something like that, and you look at some paintings that have been done throughout history, you can see that progressively we got better at drawing things. You go all the way back to like cave drawings, and even like the Egyptians. It's very basic stick figure-ish stuff. And then as time's gone on, we've gotten better and better and better. And one of the reasons we got better is because we understood the mathematics behind drawing. And the problem is this: everything that we see with our eyes is in three-dimensional space, right? So we see something, and we can perceive with our eyes this thing depth, right? This depth. We can tell which things are closer to us and further away. It is very difficult to take something like a scenery, like, you know, you go look at a field or something. It's very hard to take that three-dimensional image and transfer it onto a flat sheet of paper and trick your eyeballs into thinking you're actually looking at something three-dimensional. That's very difficult. So I'm going to try and illustrate this with an example, and hopefully you'll get the ultimate point to this. So I'm going to have two pictures, one on the left, one on the right. They're going to be the same pictures, all right? The first picture on the left is going to be a road. So we're looking from the top down. Would you all say that's a pretty good road? I'd say it is. I'd say it's awesome, yes. Okay, and then to the right of the road, there's a building, okay? And that's kind of the rooftop of the building. And then here's another building. I'll put a rooftop on that one. Here's another building. So a couple of buildings here. Okay, do you see the road and the buildings to the side? We're looking from the top down?
Yeah.
Yeah, okay. Now, in reality, if I were to go out there, would you all agree that the road, right, that's generally speaking, that those are going to be parallel lines,
Yes.
right? And so are the little dashes in the middle. Those are parallel. So none of those lines should be hitting each other. The building that's to the side, all of these lines are parallel, right? And they're following the rules of parallel lines, which are they should not hit, right? They should never intersect. But it turns out that if you want to trick the eyeball into seeing three-dimensional depth, then you have to draw in a way that breaks these rules. So now on the right-hand side comes my next drawing. So I'm drawing right here what's going to turn out to be the horizon, okay? And then I'm going to draw a point at the horizon. And from that point, I'm going to draw back two lines. Okay, there's my road. Do you see it?
Mhm.
Okay. Here's my building. Here's my other building. I'm not going to draw any more buildings. I think you get the point. Notice that all these lines that used to be parallel over here on the left, notice that those lines are now all going to a point, aren't they? Even the dashed ones in the middle are all going to that point. these lines that used to represent the edges of these buildings are also going to that point. And anybody who's done any drawing in their life, maybe someone here has, we call this, does anyone know what we call this type of drawing? Drawing in, you know, perspective? No? This point right here has a name. Anyone know the name of that point? No one's done any drawing? Taken any art classes or anything? It's called the
Not since
vanishing
middle
point.
school.
Okay. This is called the vanishing point. So we know in real life that road does not actually, the curbs don't come together and hit, right? But visually it looks like it does. And so would you agree that the picture on the right is a much better representation of what is actually there than the picture on the left? The left is a little more basic. It's following the rules though. Parallel lines don't hit. The one on the right, parallel lines do hit. So it turns out that there's different types of geometry. And the geometry that we are dealing with in this class and that you would deal with pretty much if you took any math class up until you get to like junior, senior level math classes, this is all called Euclidean geometry. Euclidean geometry. And this right here is non-Euclidean geometry in exactly, it's called perspective. Perspective geometry. So when we're sitting here and we're talking about parallel lines and we say, okay, try and explain to me what parallel lines are. And we say, oh, well, two parallel lines never hit each other. That is true. And I completely agree with you as long as we are living in this universe of Euclidean geometry. If you want to talk about a different type of geometry, then those rules don't apply. They're different. And so I'm just trying to get you to see that the world is a little bit bigger than the little fishbowl that we're living in here. In a math class like this, we always stay in Euclidean. That's our fishbowl. But there's a bigger universe out there where we use other geometries to solve problems. If any of you have heard of Albert Einstein and his famous work on special relativity, special relativity is a non-Euclidean geometry. It's a geometry that does not involve the standard rules of Euclid, which was a mathematician. It's a different type. So that's all. I just want you to understand that there's more out there than meets the eye. All right. But for us in this class, two lines are parallel if they have the same slope. All right. And that means they can't hit each other. So we're going to stick to that. I just want you to see that. Okay. Now, what about perpendicular lines? So if you were to try and explain to me what two perpendicular lines are, how would you explain that?
Like a four-way intersection.
Okay, so like
when
yeah.
they intersect, they create 90-degree angles.
Yeah, so if they hit each other like at this perfect T, right? It's a perfect like T. And if we were to measure this as an angle, we call that a right angle. It's 90 degrees. And the T doesn't have to be vertically. It could be like this. As long as it's a T, like that, then the two lines are perpendicular. So remember, parallel, they had to have the same slopes. What do you think the relationship between the slopes has to be perpendicular? It's obviously not the same, right? There's got to be some relation. What's that?
Opposite.
Opposite would be a good guess, right? So like if one of them has a slope of 3, maybe -3. If the other one had -3, then they'd be perpendicular. They'd be opposites, right? It's almost that, but it's not quite. Okay. It's close, but it's not quite. And most people are not going to be able to determine this on their own. Okay, so I just have to tell you. But opposite is the most frequent guess that I get on it. Here's what they have to be. Slopes must be opposite reciprocals. Okay, so what do I mean by that? Opposite reciprocals. So let's say I have a slope of a line that's 3. for a line to be parallel to this, I mean, sorry, not parallel, perpendicular, the slope of the second line isn't going to be 3. It's going to be the opposite of 3, which is -3, but flipped over. That's what a reciprocal is. So it's not -3, right? It's not this, but it's that flipped over. So what's -3 flipped over? So remember, -3 is the same as -3/1, right? So if I flip that over, what would it be?
One over -3.
1 over -3, which you could also write as -1/3, which you could also write as -1/3. Remember, all of those are the same. So you take your fraction, you flip it over, right? Change the sign and flip it over. And that would be what it takes for them to be perpendicular. So let's go back to this. Uh-oh. Wow, I way lost my spot here. Here we go. Okay, so back to this one. We already had said in number 20 that these were not parallel because those slopes were not the same. Are they perpendicular? So if you take one of the slopes, let's say we take this slope, -2/5. Oh, that's not a 5, that's a 3. If I tell you to flip it over and change the sign, what would you get?
+5.
Yeah, you get +5/2, wouldn't you? Flip it over. So if we flip it, it would become 5/2, and then change the sign. So instead of being negative, make it positive, and you would get 5/2. So that means that these lines are perpendicular. Okay, any questions on that?
Can we do one more?
Yeah, how about this? Y equals 4x minus 1, and then y equals -4x plus 3. Okay, are these two lines in slope-intercept form?
Yes.
So are they solved for y? Yes, okay. The slope of the first line is 4. The slope of the second line is -4. So are they parallel?
No.
No, they would have to be the same. So they're not parallel. Are they perpendicular? So take one of these, just pick one. Take 4,
Yeah.
write it as a fraction, flip it over. What happens if you flip this? 1/4.
-1/4.
And then change the sign. Is that what the other one is?
Yeah. No. No.
No, it's not, right? -4 is -4/1, not -1/4. So these are not the same. And what does that mean?
They're neither.
They're neither. Okay, this would be neither. If somebody gives you two lines, they don't have to be parallel. They don't have or perpendicular. It's not like true or false. You can have two lines that are parallel, or they could be perpendicular, or they could be neither. So there's 3 possibilities when it comes to lines.
Okay, so why was the -2 or the number 20 right here?
Mm-hmm.
When you said you flipped it over, it was +5/2, right?
So I took this slope, right? -2/5. I flipped it, right? And then I changed the sign. And when I change the sign, right, what do I get if I change the sign of this one? Instead of being negative, it's positive,
Yeah.
right?
Yeah.
And that matches exactly what that is on the second line.
Oh, okay.
And if they match, then they were perpendicular.
But how do you know to take away the sign?
That's always the case.
Oh, okay.
Always the case. So for two lines to be perpendicular to one another, the slopes have to be reciprocals, so they have to be flips of each other, and they also have to, be opposite in sign. So if one of them's negative, the other one has to be positive.
Oh, okay.
Okay?
Yeah.
Okay. All right. Let's see here. 12, 15. So these, I think, those are just asking like find the slope. Are they parallel, perpendicular? I want you to, in your homework, work through those and see how that goes. One other thing we didn't talk about, but it's being asked in the, it's going to be asked in the homework, is what the slope tells you in terms of the pitch of the line. So I'm just going to go to a new page for this. If you think about the different scenarios you can have with the line, you could have a line that goes like this, or you could have a line that goes like this. So it's kind of like if you were reading this book, like reading them as like a book from left to right, or if you think of like if you were a person standing here walking on the line, trying to walk to the right, this person on this first graph would be walking up, right? There'd be like an upward slope. Whereas on the other one, if we move from left to right, a person walking would be walking down. So anytime you have a line that pitches up like the one on the left, this is what we refer to as a positive slope. And that means that when you look at the M for that line, it's going to be bigger than 0. And this other one, you have a negative slope. And that means your M, when you look at that line, will be negative. So M is less than 0. Does anybody know what the slope of a line would be if you were flat, horizontal? Does anyone know what the slope of that line would be? So if you're walking on this, you're just walking across, you're not going up or down at all. You're just staying flat. Anyone know what the slope of that would be?
0.
0. Good. There's 0 slope. And there's one more possibility. You could have a line where it's vertical, like this. And in this case, a person walking couldn't really walk because they would fall, I guess. I don't know if there's gravity. But in this case, the slope is what we call undefined. So these are your 4 possibilities with slopes. Positive slope means you go up as you move from left to right. Negative slope means you go down as you move left to right. Slope of 0 means you're not moving up or down at all, you're just going flat. And then anytime you have a vertical line, the slope is undefined. So in that packet question that I was looking at here, it says determine if the slope is positive, negative, 0, or undefined. So what about for this first one? Would the slope be positive or negative?
Positive.
Positive. Second one?
0.
0. And third one? Negative, right? I mean, there's not a lot to those. You're just looking. Okay, there's the homework for that. Let's see, it's 12. Let's take our break right now. It's 12:15. Let's come back 12:30. Give you about a 14-minute break. That work?
Yeah. Sir, are you recording this?
Yes, I am.
Oh, okay. Okay.
Yep.
Because I have to go to an appointment, but I just want to make sure you're recording the rest
Yes.
of this.
Last time I had it set up where I had to turn on the recording each time I came in, but I've changed it now that as soon as I start the session, it's going to record. Okay.
We have a test
So-
on Monday, though?
We'll have a test on Monday, and I'll talk about that when I get. It'll be important for you to come back and look at the video because wherever I end today is where the test will end.
Okay. All
So
right.
don't assume that we're going to get through everything. I'm not sure how far we'll get.
Okay. Thank
Okay,
you.
so, all right.
All right.
All right, 12:30, we'll be back. Okay, we're going to go ahead and continue now, picking up with the next section in the packet, which has to do with functions and function notation. So we'll start this out by first understanding what a function is. So a function, which I'm going to refer to here as a number machine, is just a rule. And what it does is it takes an input, which is usually a number. It sends that number into some machine. Okay, so this is the actual function. That function does something to that input, to that number, and spits out an output. And that output is another number. So you just think of it like a car wash or something. You put something in, dirty car goes in, clean car comes out, right? Anything that you can think of that takes something in, changes it, and then spits something out the other side is kind of like a machine. So examples of functions are things like, let me write down this equation, y equals 2x plus 1. So if we look at just the x as being our input, then if we start giving this machine values of x, it's going to spit out values of y. So x is going to go into the machine, to the function, and then what's going to come out the other side is the y value. So for example, if I let x be, let's say 1, then I just replace, I take that 1, I plug it into the machine, so it becomes 2 times 1 plus 1, and that's going to just be 2 plus 1, and that gives you 3. So at the end of the day, 1 went in, went through the machine, and it spit out the other side 3. And we could do this for all sorts of different values of x. And what we can wind up doing is making what's called a t-table, and I'm sure some of you have seen this in the past. Make a t-table where you have your inputs here, and then your y value is your output here. So we already know that when you plug in 1, you get 3 to come out. And then let's just try some other values. So what happens if we plug in 2? Well, if we plug 2 into this machine, it's 2 times 2 plus 1. That'll be 4, because you have to do multiplication before the addition, plus 1, which equals 5. So if we plug in 2, we get 5. And we could keep doing this. If we plug in 3, we get 7. If we plug in -1, we get -1. You can check that yourself. But the idea is that you have an input and an output, and the machine is actually given to us by this equation. Well, whenever we have something like this, we start to use a different notation. Instead of using a y here, we replace it with the notation f of x. You know what? I'm sorry, I've been expecting this call from my wife. It's an important thing about a medical thing, so. Okay, sorry about that. My wife's having a medical procedure today. She's just calling to let me know they're about to start. Okay, okay, so we have this change in notation. So what we're going to do is we're going to write down f with a set of parentheses around the x equals 2x plus 1. And this is called function notation. And the way that you say this, like if you were verbally speaking it, you would say f of x f of x equals 2x plus 1. So it's just, all this is doing is stressing the fact that the y value can be determined as long as you give this given input of x. So you give an input of x, and this function will do something with that x and give you a result back. So in the packet, all we're being asked to do here, in this first part at least, is to take a look at a given function and then to figure out what these values are. So this first thing is saying, you know, basically that notation means replace the x with 3, or sorry, with -3, and see what happens is, you know, what comes out. So I'm going to take my equation for replace the x with -3 plus 7. So I'm going to multiply the 4 times -3 first, get -12, add 7. That gives me -5. So when we're asked to evaluate what is f of -3, the answer is -5. And that's what we're looking for. And that's it. Are there any questions on that? I mean, this is pretty straightforward. All you're doing is recognizing a new notation and then just plugging the number in for x, figuring out what it turns out to be, you're done. This next one, f of 4, means replace the x with 4. And we're still working with that same function. Okay, so it's understood. This is given to us. And then problems 1 and 2, we're just plugging in 4 for x. So this is 16 plus 7. And 16 plus 7 is 23. Okay, any questions on that? The first two are pretty straightforward. The third problem is different. The third problem is saying, find the x which gives you a value of 33. So like if we go back up and we look at the previous two problems, if I were to look at a table, number 1 said that when you plug in -3, you get -5. Number 2 said when you plug in 4, you get 23. The third problem is not asking us to plug in 33. They're saying what x gives us 33. So they're saying, like, what x do we plug in to get 33? And that's different. So the way you do this is you take your equation, and since we want to know what x is, we're going to just set the equation equal to the 33. And then we solve this equation using what we know about solving linear equations. So this is a linear equation in one variable. And so we'll just start off by subtracting 7, both sides, get 4x equals, and then let's see, is that 24? 33 take away 7. And then we will divide both sides by 4. And that will give us x is 6. So that's our answer, x is 6. So we know that if we plug 6 into the function, it's going to spit out the 33. So anytime we're dealing with functions, they can either be asking you to evaluate the function, which means take that number and plug it in, or they can be asking you to figure out what x gives you a certain value, which means you'll take the equation and set it equal to whatever value they give you. So on number 4, are they asking us to plug in 6 for x, or are they asking us to set the equation equal to 6? Anyone?
Plug in.
Plug it in. Good. So we'll just plug 6 in. How about number 5?
Plug it in.
Plug it in, right? Let me do number 5 because it's a fraction. So all we're going to do here is we're going to take our equation. We're going to replace the x with 1/8 and then add 7. And we're going to figure out what happens. So on this multiplication here, you know, just do it like this. 4/1 times 1/8 plus 7. You could then reduce this fraction, something like that. So that'll turn out giving you 1/2 plus 7. And I'm going to write 7 as 7/1 so that I can do that little cross multiply thing. 1 times 1 is 1. 2 times 7 is 14. And then over 2 times 1, which is 2. So this should give me 15/2. So if I plug 1/8 into this function, it's going to go through the function and come out as 15/2. All right. So most students do okay with that. It's not too bad. This next part that we're going to look at, hold on. Oh, you know, I was just doing the homework. Oh my gosh, I didn't realize I didn't scroll up high enough. Sorry. Oh, well, that'll help you, I guess. This next part is different. All right, so this next part, what we're doing is instead of me giving you a function, okay, and asking you to plug things in or figure out what X will give you a certain value, I'm giving you a picture of the function. Okay, so this is where students have trouble. Okay, so look, let's go back to a t-table. Remember, this all started with the idea of X equals Y, or X and Y here. Then we got rid of the Y and we replaced it with f of X. So when we look at this, if this originally was like an X and a Y, then those are like ordered pairs, right? That's an ordered pair. And so we can graph it. So I'm going to take a look at this graph, and I'm just going to start picking some points out just randomly. Can somebody tell me the ordered pair that goes with that blue dot I just put? So what is the ordered pair there? What's the X and Y? So, sorry, go ahead.
0, 4.
0, 4. So that means that, I'm going to write it over here, 0, 4. That means that the X is 0 and the Y is 4. So you could look at that as a function that takes 0 in and spits 4 out. Let me give you another point. How about this point right here? What's that point as an ordered pair?
Is it 5, 4?
5, 4. Good. So 5, 4. So that means that if you plug 5 in, it's going to spit out 4. All right. How about this point right here?
-2, 2.
-2, 2. That means if you plug in -2, it spits out +2. Let's do one more. How about this one right here?
-7, -3.
-7, -3. Good. Okay, so that means if I plug in -7, I get -3. Now, let's go and start looking at the questions. The first question is, what is f of 3? So that's asking us, if we plug 3 into this function, what does it spit out, right? So if I go to my little t-table over here, it's asking if I plug 3 in, what comes out? So you need to go find on your picture an ordered pair that has 3 here, and then you need to figure out what the Y value is there. So that means I'm going to go to the right 3, 1, 2, 3, there's 3, and I'm going to try and find the point that corresponds to that picture, which is that point right there, and ask myself, what's the ordered pair here? And I can see that, of course, the X was 3, but the output was 4. So I know that that question mark is actually 4, so that's my output. Does that make sense? Everyone okay with that?
Yes.
Okay, okay. So look at the next one, number 8. It's saying f of -3. So again, it wants me to plug -3 in for X and figure out what's coming out for Y. So I'm looking for an ordered pair that has -3 for the X and then try and figure out what the Y is. Does anyone have the answer without me showing you?
Is it 1?
Good, it's going to be 1. And that we're getting from, you're moving to the left, 1, 2, 3, that's -3. And you're trying to find a point on that picture that corresponds to -3 as your X. And you can see that red one right there. And then we ask ourselves, well, how tall was that? How high was that point? It's 1 unit up. So we know that that should be 1. So the answer here is 1. Okay. Y'all seem to be doing okay with this. Let me get rid of all this. How about the next question? You know what? I think you can do the rest. How about number 12? For what value of X is f of X equal to 3? So is this asking you to plug 3 in?
No.
No, it's not. It's saying, it's giving you the output now, right? It's saying, look, the output is 3. What's the input that gives you that? So you have to go here and look at your t-table and be like, okay, I know I'm trying to figure out what input will give me an output of 3. So when I look at my picture, I'm not going to go to 3 on the x-axis, right? I'm not going to do that. I'm going to actually go to 3 on the y-axis, which is here because that's my output. And I'm going to look to the left and to the right to try and figure out where that point is, which I just put in red. And then I'm going to kind of go down and see what x value that came from. Can you all tell what x value that is?
-1.
-1. Good. So -1 is where that comes from. So that would be the answer to number 12. It would be for what x value is it? Is the function equal to 3? We would put -1. Let's do one more of those. Let's do number 14. Number 14. So for what value of x is f of x equal to 0? So we're asking ourselves what x value gives us an output of 0. All right, can somebody see it?
-4.
-4, good. So we're looking for an output of 0. That means up and down is 0, which means we're not going to go up and down. We're just going to be here at the origin. We're going to look to our left and we're going to see that's the point right there. And now we're going to say what x value did that come from? And you can see it came from -4. So that's really asking us for the x-intercept is what that just did. We just put x equals -4. Okay, so that is all you're going to have to do on a test. All right, there's no more to that. So let me just review functions and function notation briefly. I'll give you a function, and then I'll ask you to evaluate it at some different points or at some different x values. I'll give you a y value and ask you to find the x value, and that's working just off of the function, no pictures. And then there will be a separate question where I give you a picture and I ask you to do the same things. Evaluate the function at different values and then figure out what x value gives you certain outputs. Are there any questions on that topic? Because that's it. I mean, that there's nothing more for that we're going to need to do. Okay. Now, this is your homework problem right here. The one where you're going to look at the graph. Don't worry about the fact that it's curved, okay? The fact that it's curved is irrelevant. You should still be able to pick out the points on that graph. Okay, let me just look real quick at how far we wanted to get today. Applications, yeah, I think we might be able to get through this. Okay, applications of linear functions. All right, so this is like, where can we use linear functions in the real world to help us solve problems? So let's read this first one. Mr. Thompson is on a diet. He currently weighs 260 pounds. He loses 4 pounds a month. Okay, so every month he loses 4 pounds. Write a linear model that represents Mr. Thompson's weight W after X months. And then it asks, after how many months will Mr. Thompson reach his goal weight of 20 pounds? So when I grade these on the test, part A is probably the most important part. I don't care too much. Well, I care about you getting the answer for part B, but part A is the part that I'm really interested in. So when you have a linear equation, we've seen this so far, right? That's our slope-intercept form of a line. So that's a linear equation. But we're going to be looking at this as a linear function. So we're going to take out the y and we're going to replace with f of x. So now we've got this new kind of generic thing that we call a linear function. So the word we're using now that's new is function, and that's because we're using this notation instead of y. So anytime you have a linear function, this is known as your constant, and this, the m, is your rate of change. So when you think about it, I'm going to change this, constant or start value. I'll do it. That'll be easier, I think, for y'all to understand. So think about it this way. We know that if we graph this, it's going to be a line, and we know it's going to hit here at B. Okay. So if we're thinking as X being like time on a watch or something, if X is like time, then when X is 0, right, this Y-intercept has the coordinate 0B, that's always going to be your starting value. And then the M is going to tell you how much how much whatever quantity you're measuring is going up or down. And M could be negative, so you could go down, right? Positive slope goes up, negative goes down, but that's always going to be your rate of change. So when we go and we look at this question about Mr. Thompson and his diet, we want to set up a linear equation or a linear function or a linear model where his weight is some function of X. In other words, his weight is a function of X, where X is in months. So his weight is measured in pounds and X is measured in months. And we're going to do this with a linear model. So I'm going to write it like this. Weight is equal to mx plus b. So do we know anything in terms of the word problem, like these values 260 and 4 pounds per month? What do those represent? So like, what does the 260 represent to us in this problem? Anybody?
The W?
Okay, that is his weight at the beginning though, right? That's his weight at the start. Do you agree with that?
So the F?
So go back and look at this right here. When we have a generic linear function,
It goes where MX is.
the B, right? The B is always your starting value of whatever it is you're looking at. And then the M is your rate of change, how much that value is changing. So for Mr. Thompson, the 260 is actually his starting weight. Do you all agree with that? That's where his weight starts at, starting weight. So that should be the B, 260. Now, what does the 4 represent?
Rate of change?
That's the rate of change, right? He's losing 4 pounds every month. He's losing 4 pounds every month. So I'm going to put here what number in front of X?
4.
4, yes, but he's losing that weight.
-4?
-4. So I'm put -4X. That should be what his weight is. Now, this is our first example. So let's box this up and let's think about this right now. W is his weight and X is the number of months. So what would happen at X equals 0? How many months have gone by? If X is 0, how many months have gone by?
None.
None, right? So how much should he weigh?
Same, 260.
260, right? And you can see that if I let X be 0 here in that little yellow part, if X is 0, that's gone. And then it's just saying W equals 260. So that's his weight. Okay, now what's his weight after 1 month? Well, if X is 1, then what's going to happen if you replace that X with 1? You'll be subtracting 4, right? You'll be subtracting 4 from 260. So he'll weigh 256? Do y'all see that? And then if I plug in 2, it'll be less, and 3, it'll be less, and 4, it'll be less. Every time X goes up, his total weight's going to continue to go down, but it started at 260. Does that make sense?
Yeah.
Okay. Now, that answers part A. Okay, that's part A's answer right there. So for part B, it says, after how many months will Mr. Thompson reach his goal weight of 220 pounds? So think of this as an ordered pair. We have X goes in and weight comes out, right? That's the way this is kind of set up. The X is the number of months that goes in, and then the weight is what's coming out. So in part B, what are they're asking for how many months it's going to take for his weight to be 220. So which of these two values do I know? Do I know the X or do I know the W? We want his goal weight to be 220. Go ahead.
Oh, you know the W.
We know the W, right? So for part B, what they're saying to us is this. We want to know what the X is, right? It's a question mark. What is the X that's going to give us 220? Now, this is very similar to the problems we were just doing, where we had a T-table. You know, we were saying, you know, X is here and 220 is here. And we're like, well, what's the X that gives you 220? How did we do that? How did we actually go about doing that? We did it right here, right? Like when we wanted to know when the function was equal to a value, we set the equation equal to that number, right? That's exactly what we're going to do here. We're going to take the equation, which is this, right? That's our equation. And we're going to replace the W with 220. So we're going to write 220 equals negative 4x plus 260. Okay, so we're taking that equation, we're replacing W with 220, and we're going to solve that. Now I'm going to run out of room, so I'm just doing it on the side here, and then I'll erase it. We want to know when 220 equals negative 4x plus 260. So I need to solve for x here. So I'll subtract 260 on both sides. That'll give me negative 4x equals negative 40. And then I'll divide both sides by negative 4. And I'll get 10. Because negative 40 divided by negative 4 is positive 10. So it will take 10 months for him to get to his goal weight of 220 pounds. Okay. So we're going to skip number 2. Let me ask you a question on number 1. Could you tell me how much you'd weigh in 2 years? So like if I added a new question to number 1, if I added a part C, let's say, I'm gonna throw it right here. You know, how much does he weigh after 2 years? What would you do with the equation?
Would you replace X with 24?
Exactly. You'd replace X with 24. So here, when we say 2 years, well, that's 24 months, right? So if we go to this equation and we replace the X with 24, we could figure out what that is. Actually, he might be dead. No, well, he might be dead. Let's see. Negative 4 times 24. That's not bad, 96 pounds plus 260. He'd weigh 164 pounds. Okay. All right. Let's see. I'm going to see if I can find something real quick. I'm going to show y'all. So back before I got married, I was pretty athletic. And I did a lot of triathlons and stuff. And I was really big with cycling. I used to ride a lot of miles on my bike. And so I'd go into these phases where I would start losing weight, you know, like I would enjoy life for like 3 months, eat whatever I want, do whatever I want, and then I'd get really healthy and lose a lot of weight. So, oops, did not do that. Let's see here. Okay, we'll just have to use that one. I'm gonna try and share this with y'all here. Bring this down here. I normally don't ever share these things with my students, but okay, so I know that that's very difficult to read, okay? But I would get up in the morning, I'd weigh myself, right? I would keep track of what I'm eating. I'd keep track of how many miles I went, how many calories I burned, all these different things. And so what I would do is I'd take my weight each day, and you can see I was really kind of overweight. I mean, for me, I was up to like 197 pounds, which is a lot. And for me, it was a lot. So I would track every day, and you can see how I slowly started to chip away at my weight, right? And whenever you keep track of things like this in a program like Microsoft Excel, you can have the program automatically give you a linear function that will give you like your slope and Y-intercept. And this is it up here in this top corner. You can see this. And that negative 0.2861, that represented my change in weight per day. So that's telling you that I was losing over a quarter pound a day. So every day, almost a third of a pound is what I was losing. So in 3 days, I'd lose 1 pound. And I did that for, you know, basically 6-7 weeks. And I was able to drop from 197 down to 178. And then I let it go again and then came back. But anyways, my point is that this linear equation right here tells me everything I need to know about how my weight loss is going. It's that slope, that M in front. The bigger that M is, the faster I'm going down, right? The bigger it is in terms of, you know, a negative number meant it was going down. If it were positive, it'd be bad because I'd be going up. So anyway, I'm just sharing that with you because there's software out there that if you take any data, it will automatically find that line for you, and it'll give you all the information. Those are called regression models. So what we did here for Mr. Thompson is we basically had his weight loss model here, and we tried to predict how much he would weigh in the future or how long it would take him to get to a certain weight. And that's pretty much what I would do. I would have a goal weight. You can see my goal weight down here was 174. And I don't think I ever reached it, but I could see by this line when I would reach it. I should have reached it in week 11, but I don't think it happened. Okay, sorry about that. I'm just trying to show you like something practical, I guess. May not seem practical to you, but.
That's cool.
Yeah, when I used to do triathlons, I weighed 168, usually 164 to 168, which is like super too thin. My wife hated it when I do that stuff, but okay.
What's your height?
I am 6'2", 6'1".
Oh my God.
Yeah. Yeah, 165 is like really, really thin for 6'2".
Yeah.
Yeah. Yeah. When you're riding a bike a lot, you don't want to have any extra weight. So it was pretty normal to be, like if you look at cyclists and stuff, If you just go and look at, like, I wasn't a professional athlete, but professional athletes that are cyclists look like emaciated, like really bad. Do y'all know who the top cyclist in the world is right now? Probably don't. No. Oops. So Chris Froome is by far the strongest cyclist in the world. He got injured this past year, so he didn't really get to compete in the big tour. But give you an idea of, let me just put in here, skinny. Let's see what it comes up with. Yeah, so this is him competing in the Tour de France, right? And he looks kind of like he should be on his deathbed, right? Would you all agree? Chris Froome, stats. Let's see how much he weighs. Oh, wait, I just saw it there. So he's 6'1", right? He weighs 146 pounds. That's crazy.
That's
Yeah, that's crazy. But he's the strongest cyclist in the world. He can go up the mountains and nobody can keep up with him, because everything he has is, you know, muscle in the heart. His heart and his lungs are just so much more efficient than everyone else's. Okay, I've gone way off topic. Sorry. Let's get back to this. Okay, let's not worry about number 2. Let's look at number 3. Kara uses a linear model. F of x equals 20,000 plus 0.3x. So that's kind of like the model that I have for my weight. We're given that information. She does that to predict her total salary from achieving a total sales of x. Interpret the slope and y-intercept in terms of her salary and sales. Okay, so let's just take our time through this. First of all, we need to understand what x is in the problem. And here it says x is her total sales. Okay, so the input to this function is how much she's selling at her job, whatever it is. And the output, okay, f of x is her total salary. Okay, so this is f of x. Her total salary is a function of how much she sells. So it says interpret the slope and the y-intercept in terms of her salary. So can somebody tell me what is the y-intercept? Let's start with the y-intercept. What is the y-intercept of this function?
$20,000.
20,000. And what does that y-intercept represent in terms of her salary and sales? How could you interpret that 20,000 for me?
Base salary.
That's like a base salary. Very good. So that's her starting salary. That's if she sells nothing. So maybe she sells, I don't know, cars. I'm not sure. Whatever she sells, cars, she's selling. We had a girl the other day contact us. She was selling knives, those Cutco knives, whatever it is. Whatever she's selling, if she sells 0, she's still going to make $20,000 just for going around and trying to sell stuff. Okay, that's her base salary. So the 20,000 is her base salary. Okay, and then what would the slope represent then? So what would this 0.3 represent? That's the slope. This is a trickier problem, so I think I'm going to answer it this first time for us. The 0.3 is the rate of change of her total salary. So what would happen if she sold $10 worth of stuff? We would replace that x with 10, right? And what's 10 times 0.3? Just move the decimal point over one place and you would get 3, right? $3. So she makes she makes $3 if she sells $10. What would happen if she sold $100? She wouldn't make 3, she'd make what?
30.
30, right? So that 0.3 is like a percentage, right? She's making an additional percentage. What would 0.3 as a percentage be? Like if I ask you to convert that to a percent.
1/3.
30, the decimal point comes over 2 places, right? So the slope represents a 30%. Does anyone know what it's called for people who are in sales? When they get a certain percentage of their sales, what that's actually called?
Commission.
Commission. I think I spelled that right. Doesn't seem right. Commission. So in this particular model, the 20,000 is her base salary, and the 0.3 in front of that X is her percentage of commission. So she makes 30% on everything she sells. She sells $10, she gets $3. $100, she gets 30. $1,000, she gets 300. So 30% commission. Okay, let's do number 5. I'm going to let you take a look at number 4 yourself. 5 has caused problems for people in the past. So Joe has a part-time job caring for and walking dogs, which I guess is a job you can have nowadays, right? He estimates that his annual insurance is $420. So he has to pay for insurance in case he's out walking a dog and one of them gets away from him, gets hit by a car, and then the person he's working for sues him or something, right? So he has this insurance to protect him in case something goes wrong. He has to pay $420 a year for that. On average, he spends $4.50 on gasoline for every visit he makes. So when he goes to walk someone's dogs or take care of them, every single time he goes out to do it, on average, he spends about $4.50. He charges $15 to go walk their dog. So it says, note that this is an annual cost function. So the first question is, what is the one-time annual charge or fixed cost? So can somebody tell me what his fixed cost is, what he's going to have to do no matter what every year? How much he's going to have to pay?
420.
420, right? If he wants insurance, right, it's going to be $420. Okay. What is the variable cost?
The 450.
The $450, because the variable cost is, well, he doesn't always have to pay $450. He only has to pay $450 if he actually goes and does a job, right? But it's going to cost him $450. So now it asks for us to find the cost function. Okay, so it wants us to write a cost function. So they use capital C. Instead of the little f, they use capital C for cost. It's just a generic letter. You don't have to worry about it. It wants us to know how much it's going to cost him to run his business, right? How much is it going to cost him to run his business? Well, we already know that there's a fixed cost of $420, no matter what, right? But in addition to that, he's also going to have to pay $4.50 for every time he walks a dog or takes care of, walks a dog. So X is the number of jobs he does, right? Do y'all see how that cost function goes together? You have the fixed cost of $420 no matter what. And then in addition to that, each time he does a job, you have to multiply it by 450 and add that to the cost. Is that clear to everyone? Or are there any questions on that? What information did we not use in this
The
problem?
$15 per visit.
Yeah, the 15, we didn't even use it, did we? Because we weren't asked about it. Now, there is something that we could include in this, which would be revenue and profit, but it wasn't asked, and this is not a business math class, so we're not going to get into revenue and profit. So we're just going to answer the question and move on. All right. The big thing is I wanted you to see that this $15 did not play a part in this question at all. So sometimes there's information there that's irrelevant. Okay, we're gonna finish that section for now because I want to have a little bit of time at the end to talk about the test. Mixtures. I'm just contemplating whether or not I want to put this on the test. I think I do. Some of these problems are a little bit tough. Looking at the clock, I think we have enough time. All right, let's see how this goes. Mixture problems always cause students issues. All right, so I'm trying to start this out with as easy of an explanation as I possibly can give you. So let's say I have a container that has water in it, okay, and salt. So you know that when you put salt in water, you stir it up, you don't see the salt anymore, right? It's been dissolved, but it's still in the water, but it's mixed in. So let's say I have this container. Let's say that that's a 3-liter container. So I'm going to put 3L, all right? And let's say that it is 15% salt. The way I want you to visualize that is that you have this liquid in here, right? There's liquid, it's all liquid in there. 3 liters worth of this salt water. If you were to be able to separate and see visually the salt in here and put it, let's say, on the bottom, you would have this like little layer of salt down here, right? So that would be your 15%. Even though it's like swirled around in the water, like if you could separate it, you would have part of it would be water and part of it would be salt, right? Let's say we take that container and then let's say we have another container. Let's say that container has, I don't know, I'm going to make this up, 5 liters of a 20% salt mixture. So again, we have all this water in here, and then there's a certain percentage of it that is salt, right, on the bottom here. Of course, it's swirled in together. So what would happen if I take both of these containers and pour them together into a bigger container? What would I get? Okay, so that's the question. If I take these two, I pour this one, everything in that one, into this new container. The question is, how many liters would I have, and what would the percentage of salt be? Does the question make sense? Is everyone okay with that?
Yeah.
Okay, so let's start with the easier of the two questions. Which is the easier of the two?
How many liters there are?
Yeah, how many liters are there? Well, we poured them both in there, and how many liters were in each? 3 and 5, right? So this one should just be straightforward. This is 3 liters plus 5 liters. So we should have an 8-liter mixture. Do you all agree with that? With 8 liters of mixed stuff. Now, to find the percentage of salt, that's the more challenging piece, all right? So the way this is done is that you go back to the original given information on that first container right here. So let me ask you this way. I'm going to change it so it's a little easier. What if I told you you had 3 liters and it was 50% salt? 50% salt. Then how many liters of salt would you have in there?
1.5.
1.5, right? So it'd basically be 1.5 of it would be water and the other 1.5 would be salt. So there's a way that you can figure out how many liters of salt there are by knowing the percentage. What if I told you you had 3 liters, right, mixed, but 10% of it was salt? How many liters of salt would you have? So if it was 50%, I think most people were like, oh, just half it, right? But if I told you it was 10% salt, what would you do to figure out how many liters of salt you have? It's a little bit more difficult, right? So maybe if I do it this way, if I said 3 liters and 50% salt, I think most of you are okay with the idea that if that were the case, then you have 1.5 liters of salt, because half of it's salt and half of it is water. The way you can get this number is by taking these two and multiplying them together. Think about this. What is 3 times, what is 50% as a decimal?
0.5.
0.5, right? 0.50. And if you multiply those together, voila, you get your 1.5. So when we go back here, I'm going to just forget that for now. When we go back here, if I want to know how much salt is in there, what I'm going to do is I'm going to take my 3 liters and I'm going to multiply it by the 15%. I'm going to do that right here. 3 times 0.15. So I have to convert 15% over to a decimal, which would be 0.15 times 3. I don't know why I'm doing this on my calculator. I really don't need to do that, but I did. This is 0.45 liters of salt. Is that okay?
Yeah, so it'd be
So,
5%.
pardon me?
Will it be 45%?
No, we have 3 liters of mixture, right? Part of it is water, part of it is salt. If you could separate the salt out, you would have 0.5 liters of salt. If you could pull it out, okay? So that's how much there is in red here. It's 0.5 liters of salt. Now, what about on the second container? How much salt is here? So do the same thing. 5 liters times that. So that's the same as 5 times 0.2. And what would that give you? Should just get 1 liter. So that's how much salt you have here. So now, when you look at this mixture now, you know that there is a bunch of water in here, but now you know you also have the salt in here. The salt came from both containers in here. How much salt is in there? How many liters of salt has to be here? What's the salt from both containers, right? So how much is that? Sorry, I didn't hear you. No? How many liters of salt come from the first container?
1.45.
Okay, so from the first container is 0.45, from the second container is 1. So you put those together, our new mixture should have 1.45 liters of salt. Now remember, we were trying to figure out what the percentage of salt was, right? And if you go back to when we learned percentages, a percent is always the part that you're looking for divided by the entire thing. We said it was part over whole. So a percent is the part that you have of something divided by the whole thing. So do we know what part of this is salt? Yeah, 1.45 liters. Do we know how many liters we have whole in the whole container?
Yes.
8, right? We already determined that. So if we do that on our calculator, 1.45, and divide that by 8, we get 0.18125 is what I'm getting, which is about 18.125%. Ooh, it's messy, yes? I think we should maybe do one more.
Yes.
Are there any questions on this one before I go to the next one, though? Like where I got anything? I mean, I'll kind of try and recap it. What you're doing is there's two parts to the problem. You first have to figure out how much stuff you have total. When you mix the two together, how much did you have? We said 8 liters. That was pretty straightforward because we did 3 liters and 5 liters. The second part is trying to figure out what we call like the concentration of each of these batches. So we had a certain concentration, 15%, and another concentration, 20%, but we had to convert those over to liters so we could figure out how much of that goes into the mixture and then take that and divide it by the whole to get our percentage. So it's multi-stepped problem. I'm going to look at number 11. Okay, 20 pints of 2% saline solution. Saline solution is salt water, basically, is mixed with 15 pints of 9% saline solution. How many pints are in the final mixture, and what is the percent of saline? Okay, this is exactly the same type of problem. So I like pictures. So I'm gonna draw my first picture. I have this container. How many pints are in the first container?
20.
20, right? So we have 20 pints. I'm gonna put 20p. And what is the percentage? 2%, right? And we're gonna be adding that to another container that has 15 pints of 9% saline solution. When I add those two together, I should have this new container that has how many pints in it? So that part shouldn't be hard. 35 pints, right? So that's how much total, because I took the 20 and the 15, added them together. The question is, what's the percentage? So this is where you have to go in here and just go, okay, I need to find out what 2% of 20 is and what is 9% of 15. That's going to give us how many pints of salt we have. So on your calculator, 2% of 20, you should get, so I'm doing 20 times 0.02. Be real careful to make sure 2% is converted properly. You should get 0.4 pints. And then on the next one, we're going to do 15 times 0.09. And yeah, I better do that one on my calculator. So 15 times 0.09 gives you 1.35 pints. So how many pints of salt are in the mixture? So in this mix over here, how many pints of salt do we have? Just add these up, right?
1.75.
Okay, we have 1.75 pints of salt. Now that's not a percentage, right? What we now need to figure out is the percentage of salt in this mixture, so we have to do the part over the whole. And to do that, well, the part that we have is 1.75, and we divide that by the whole thing, which is 35, and that should give us our percentage. Well, it should give us a decimal. I get 0.05, which as a decimal is 5%. Does that help a little bit, or y'all still lost on that? Should I do one more?
I'm good.
You good? Okay. Maybe I won't do the whole problem, but let me just look at number 12, because number 12 is a little bit tricky. There are 2 liters of 3% milk. So I have 2 liters of 3% milk. I don't like that. Of 3% milk, which is mixed with some 1% milk. So this is 1%, but they don't tell you how much. And it's mixed together, right? And it says if there are 7 liters of the mixture, so they say 7 liters over here, how many liters of 1% are there. So they want to know how many liters do you have here? And then they want to know what the percentage is here. So this problem is not harder. It's just a little bit trickier because they don't tell you how many liters are in the second one. But you can figure it out pretty easily because you know that they add up to be 7. So how many liters of the second mixture or second 1% is there?
5.
5. It's just 5, right? Because 2 plus 5 is 7. So once you're here, you can do everything else we did before in the previous problem. So just be careful with the wording. All right, let's talk about exam. Where's my thing here? There we go. Give me a moment to open this up. I may not have this here readily available, but I'm hoping I will. I do. Yeah, I don't see a second exam here. Yeah, you know what? I'm going to have to go look for it somewhere else. And I don't want to make y'all have to wait for me here. So just to be clear, our exam will cover everything from scientific notation down to mixtures, right? It'll be on Monday. Why don't we do this? On Monday, let's plan for the first, let's say 15 or 20 minutes of class will be a question and answer session. So I can clarify anything, all right? And then I'll start the exam. Let's say we start at 11. Let's say the exam will start, somewhere around 11:15 to 11:20, somewhere around there. So, I encourage you to be there at 11, okay? That way I can answer questions, because if I get into class and no one has questions, we're just gonna start the test. But I will allow up to 15 or 20 minutes to answer any questions. And that way, if you run into anything on your homework or something like that, you want clarification, you can get that at least before the test. I'm going to, as soon as I close this session out, I'm gonna go see if I can find something like, not a review, but something for you to use as a guide to prepare for the test. And I'll do that pretty soon, okay? And that way over the weekend, you can at least have something to go off of. But remember, just practice your homework. And if you feel good with that, you should be okay. There's gonna be word problems on this test, so I think it's gonna be harder than the first one. But if I provide you a review or something to look at, I probably will not provide you with answers. And that's what I'll spend the first 15, 20 minutes of class doing, is just clarifying anything, or if you want to verify that you did something right, I can do that then. Does that sound okay to everyone?
Yes.
Okay. Okay. So I'm going to close this session out. I'm going to go look up that review, and I'll get that sent out pretty quick. And then I will see you all on Monday at 11, and we'll do the test. After the test, we will be going and talking about factoring and solving equations by factoring. We'll see how much time we have, but I think this next test I'm going to be giving you a little bit more time than I did on the last one, but we'll just see how it goes. But, all right.
Oh, I have a question real quick.
Yes.
On that last one we just did, so I got 0.11.
Which one? The
when
one I
added the two
started, or the one I?
Yeah, the one you started.
Okay.
Okay, so I got 0.11 as far for the part, and the whole is 7 liters. And I divide the 0.11 by.
You're cutting out.
I was saying, and so once I got the 0.11
Uh-huh.
for the, and then I just do the part over the whole, right? So 0.11 over 7.
Yep.
And I didn't get the right answer.
What did you get? 1.5?
I got like maybe this is what I did wrong. So 0.11 divided by 7. Oh, okay. Never mind. I don't know what I did wrong. I just got the right answer.
Typed it in wrong or something?
Yeah, I'm doing it on my phone instead of my calculator, so
Gotcha.
maybe I did something
Okay.
different.
Yeah, should be about 1.57% or something like that.
Yeah, that's what I got.
Okay.
And you said you're gonna send out or you're gonna put the review on file or something on the files?
I'll send it as an email through Canvas.
Thank you.
Okay. Any other questions? No? Okay, well, we'll call it a day. Y'all have a good one.